Hi friends, in this class we will study reciprocity theorem in the series of network theorems. The term reciprocity means something interchanging. You will understand more when we are going through the definition, explanation and doing some examples. Reciprocity theorem. It states that in a linear, bilateral, active, single source network. See, this single source network, it is a very important term. The ratio of response to this excitation remains the same even when the positions of this response and excitation are interchanged. That is, when excitation goes here and the response comes to this side. For applying the reciprocity theorem, certain conditions must be satisfied. Conditions for applying reciprocity theorem. The ratio of response to excitation is either ohm or mho. In this case, we have taken response to excitation, that is I over V, which is mho. Second condition is only one independent source must be present in the circuit. Third one is no dependent source must be present in the circuit. This is an independent source. No dependent source must be present in the circuit. Next, this is applicable only in linear and bilateral networks. That is, be careful, we are changing only the excitation and response. We are not changing the positions of these components inside this network. That is, in the circuit, positions of any passive elements R, L, C must not be changed, only excitation and response can be interchanged. Now we will see some examples. In example 1, we are asked to calculate the current I and verify the reciprocity theorem for the given network. See here, this 20 volt is the excitation while this current I is response. We have to find the response I when excitation is 20 volt. In the case 1, we will solve the circuit when the excitation is 20 volt and response is I, which are not interchanged. We will solve it using mesh analysis. We know that for applying mesh analysis, we have to first mark the meshes, then the currents. Current in mesh 1 is I1 and current in mesh 2 is I2. Then we have to mark the polarities of the current flow in these resistances. As in mesh 1, current is flowing in this way. It is entering here, that is, here it is plus while this is minus. In this resistance, it is entering here plus and this is minus. In mesh 2, I2 is entering here plus and this is minus, plus, minus, plus, minus. Applying KVL to mesh 1, according to Kirchhoff's voltage law, algebraic sum of these EMFs and voltage drops in a closed loop will be 0. Here, as current is going in this direction, it is rise in potential, so it is plus 20 volt. Then here, plus to minus, that is voltage drop minus 5 into I1. Then here plus to minus, there also voltage drop is there, 10 into difference of these two currents, I1 and I2. As we are in mesh 1, we will write I1 first minus I2. This is equal to 0. Simplifying this equation, we will get 15 I1 minus 10 I2 is equal to 20. Let this is equation number 1. Similarly, applying KVL to mesh 2, minus 4 into I2, then drop in 6 into I2 minus 10 into difference of I1 and I2, that is I2 minus I1, as we are in mesh 2. Minus 4 I2 minus 6 I2 minus 10 into I2 minus I1 is equal to 0. Simplifying this one, we will get 10 I1 minus 20 I2 is equal to 0. Let this is equation number 2. Solving equations 1 and 2, we will get I1 is equal to 2 ampere and I2 is equal to 1 ampere. But here see, actually I is the mesh current I2, that is I is equal to I2, which is 1 ampere. Then case 2 is when this excitation and response are interchanged. That means this 20 volt will go here and this I will come here and our circuit becomes like this. See, excitation has gone here and response came to this part. As we have done earlier, here also we will apply mesh analysis. For applying mesh analysis, we have to mark the meshes as 1 and 2, then current flowing in clockwise direction. In mesh 1 is I1 and in mesh 2 is I2. Next we have to mark the polarities of these resistances. As current is flowing in this way, it is entering here plus, while leaving here it is minus, plus, minus, while in this mesh it is entering here plus, minus, plus, minus, plus, minus. That is, voltage drops are there in these resistances. Now applying KVL to this mesh 1, algebraic sum of EMFs and voltage drops in a closed loop is equal to 0. Here voltage drop is there, so minus 5 into I1. See here I1 is in this direction, I2 in opposite direction. So the difference of I1 and I2 we have to take. As in this resistance I1 is going from positive to negative, minus 10 into difference of these currents. I1 is to be taken first, minus I2 is equal to 0. Simplifying this equation, we will get minus 15 I1 plus 10 I2 is equal to 0. Let this is equation number 1. Next applying KVL to mesh 2. See here in this resistance voltage drop is there. So minus 10 into difference of these currents as they are in opposite direction. As we are in mesh 2, we have to write I2 first, minus I1. Next voltage drop in 4 ohm, minus 4 into I2. Then here fall in voltage is there, plus to minus. So minus 20. Then voltage drop in 6 ohm, minus 6 into I2 is equal to 0. Simplifying this, we will get 10 I1 minus 20 I2 is equal to 20. Let this is equation number 2. Now solving equations 1 and 2, we will get I1 is equal to minus 1 ampere and I2 is equal to minus 1.5 ampere. But see here I1 is in this direction. So I is equal to minus of minus I1, that is minus 1, which is 1 ampere. In case 1, we got I is equal to 1 ampere when it was on right side, and case 2 when excitation response are interchanged, here also we got I is equal to 1 ampere. Since current remains the same in both cases, reciprocity theorem is verified. Here we are asked to verify the reciprocity theorem for the network shown here. First we will simplify the circuit containing this much resistances so that the total current we will find out first. Here excitation is given as 20 volt and the response is current I. First we will take the case when excitation and response are not interchanged. See here this 2 ohm and this 2 ohm are in parallel. Effective resistance becomes 2 into 2 divided by 2 plus 2, that is equal to 1 ohm. So we can redraw this circuit as like this. See here this 20 volt is here, this 2 ohm, 3 ohm, this 2 ohm, and this is the 1 ohm, which is the parallel combination of these two resistances. Now see this 2 ohm is in series with this 1 ohm. That means we can add it so that it becomes 3 ohm. So our circuit becomes like this. Again see here this 3 ohm and this 3 ohm are in parallel. That means 3 ohm in parallel with 3 ohm, which is equal to 3 into 3 divided by 3 plus 3, which is 1.5 ohm. So this 2 ohm will come in series with this 1.5 ohm. So this circuit can again be written as like this. This voltage source was there, then this 2 ohm came in series with this 1.5 ohm, which was the parallel connection of 3 and 3. That is, the total resistance becomes this 2 plus this 1.5, that is 3.5 ohm. So the total current flowing will be IT, that is our voltage 20 volt divided by total resistance, that is 3.5, which is equal to 5.71 ampere. That means the total current IT, which is coming from 20 volt, which is 5.71 ampere, splits up into two resistances which are parallelly connected. As these two resistances are of equal value, the total current coming will be equally distributed through the two resistances as they are of the same value. Therefore, current flowing through these two resistances are 5.71 divided by 2, that is equal to 2.85 ampere. We know that this is the combination of these 2 ohm and 1 ohm. So this 2.85 is going through this branch and this branch. So this 2.85 which comes here is going through 2 ohm and this 1 ohm, as they are connected in series. So current in this 1 ohm is 2.85 ampere. This diagram we got after the combination of these two resistances which are in parallel and the value is 1 ohm. See, the 2.85 which is coming here is going into these two resistances which are in parallel, that is 1 ampere. So total current flowing through these two resistances which are in parallel is 2.85, and as they are of the same value, the current in each resistance will be the total current 2.85 divided by 2, that is I is equal to 2.85 divided by 2, which is equal to 1.43 ampere. Therefore, current in this 2 ohm resistance is 1.43 ampere. Here the excitation was 20 volt and response we got as 1.43 ampere. Therefore, ratio of response to excitation is 1.43 divided by 20, which is equal to 0.0715. When excitation and response are interchanged, our circuit becomes this side. The excitation 20 volt comes to this side, while the response I comes to this side. As this 2 ohm and 3 ohm are in parallel, the effective resistance of these two becomes 2 ohm in parallel with 3 ohm, which is equal to 1.2 ohm. So that our circuit can be drawn as like this. See, the excitation is here 2 ohm, this 2 ohm is there, this 2 ohm is there, and these two parallel 1.2 ohm. Now, as this 2 ohm and 1.2 are in series, the effective resistance is 2 plus 1.2, which is equal to 3.2 ohm. So our circuit comes like this. Now this 3.2 and 2 are parallelly connected, that is 3.2 ohm is in parallel to 2, which is equal to 1.23 ohm. That means the combination of parallelly connected these two resistances gives the value 1.23 ohm. This 1.23 ohm and this 2 ohm which are in series can be added and it gives a value of 3.23 ohm. That means the circuit becomes like this. This 3.23 is the combination of seriously connected 2 ohm and this 1.23 ohm. So the total current I total will be equal to this 20 volt divided by 3.23, which is equal to 6.19 ampere. The total current of 6.19 ampere which is coming from here is dividing into 2 as per the value of these resistances. Applying current divider rule, the current flowing through this 3.2 ohm is the total current coming into value of the other resistance divided by total resistance. That is, current through 3.2 ohm is current through 3.2 ohm is equal to total value of current, that is 6.19 into the other branch resistance 2 ohm divided by total resistance 3.2 plus 2. This gives 2.38 ampere. That is, the current in this branch is 2.38 ampere. This 2.38 ampere which is coming in this branch is flowing through 2 ampere and 1.2 which are connected in series, which means that the current in 2 ampere and 1.2 ampere are both 2.338 ampere. So see, in this circuit this total current 6.19 ampere comes here as 2.38 ampere and divides into these two. The current flowing through this 2 ohm resistance is I is equal to, as per current divider rule, that is total current, that is 2.38 into resistance of the other branch 3 ohm divided by total resistance of these two branches 2 plus 3, which is equal to 1.43 ampere. So we got current in 2 ohm resistance is 1.43 ampere. Therefore, ratio of response to excitation is 1.43 divided by 20, which is equal to 0.0715. In case 1, when excitation was in this side and response was in this side, ratio of response to excitation was 0.715. In the second case also, we got ratio of response to excitation as 0.715. As in both cases, ratio of response to excitation is same, reciprocity theorem is verified. In example 3, we are asked to find this voltage V when 10 ampere source is there, and then we have to verify the reciprocity theorem for the network shown. Here this 10 ampere is the excitation and this V is the response. Case 1, we will find the response when this excitation and the response are not interchanged. For that, we will apply mesh analysis. We will redraw this circuit once again. For applying mesh analysis, we have to first mark the meshes. Here 3 meshes are there, 1, 2 and 3. Next step is to mark the currents flowing in these meshes. Let the currents are flowing in clockwise direction. Let I1 is the current flowing in mesh 1, I2 is the current flowing in mesh 2 and I3 is the current flowing in mesh 3. Next, let us mark the polarities of the voltage drops in these resistances. See, in mesh 1, as current is flowing in this way, here current is entering, so this is plus and leaving point is minus. Then current is entering here plus, leaving point minus. In mesh 2, in 4 ohm resistance, current is flowing in this way, so here it is plus, this is minus. In 2 ohms plus here and minus here. In 5 ohm it is plus here, minus here. In mesh 3, here current is entering plus, leaving minus, plus, minus, here it is plus and minus. In mesh 1, current source of 10 ampere is there. The mesh current I1 will be equal to this 10 ampere. That is, I1 is equal to 10 ampere. Applying KVL to mesh 2, algebraic sum of EMFs and voltage drops in a closed loop is 0. Therefore, in this 4 ohm voltage drop is there. Therefore, minus 4 into, as we are in mesh 2, IT is to be written first, minus I1. Minus voltage drop in 2 is 2 into I2, minus voltage drop in 5 ohm is 5 into, as we are in mesh 2, I2 minus I3 is equal to 0. Simplifying this one, we will get 4I1 minus 11 I2 plus 5 I3 is equal to 0. Let this is equation number 1. Then applying KVL to mesh 3, drop in 6 ohm is minus 6 into I3 minus I1, voltage drop in 5 minus 5 into, as we are in mesh 3, we have to write I3 first, minus I2 which is in opposite direction. Then voltage drop in 8 minus 8 into I3 is equal to 0. When simplified, this becomes 6I1 plus 5I2 minus 19I3 is equal to 0. Let this is equation number 2. I1, we already know that it is 10 ampere. Substituting the value of I1 in these two equations and solving, we will get I1 is equal to 10 ampere, I2 is equal to 5.76 ampere and I3 is equal to 4.67 ampere. See here, the voltage V is equal to I into R. The resistance is 5 ohm and the current flowing is the difference of I2 and I3. The value of I2 and I3 we found out here. So, V is equal to 5 into difference of I2 and I3. That is, V is equal to 5 into I2 minus I3. That is equal to 5 into 5.76 minus 4.67, which gives the result 5.43 volt. In the next case, we will change the excitation and response. That is case 2, when this excitation and response are interchanged. Now this 10 ampere current will come here and we have to find the voltage coming here. When these are interchanged, figure become like this. See that 10 ampere current came here and the voltage which was earlier here has gone to this place. That is, excitation came here and voltage has gone to this place. Current source in parallel with this resistance can be transformed to voltage source in which the voltage is coming in series with a resistance. When transforming from current source to voltage source, the resistance of both remains the same. That is, here R was 5 ohm, so R is equal to 5 ohm, while this voltage V is equal to I into R, that is 10 into 5, which is equal to 50 volts. After converting this current source to voltage source like this figure we can redraw as like this. See, this current source we have converted into a voltage source. Then for applying mesh analysis, we have to mark the meshes. Here 2 meshes are there and we will mark it as 1 and 2. Then we have to mark the currents flowing. Let us mark the currents flowing in clockwise direction. In mesh 1, I1 is the current flowing and in mesh 2, let I2 is the current flowing. Then we have to mark the voltage drops by marking the polarities. Here it is plus, here it is minus, as current is flowing in this direction. Similarly, here it is plus, here it is minus, and in this 5 ohm it is plus here and minus here. In mesh 2, plus is coming here, minus as current is in this direction. Then in 6 ohm plus minus, and in this 5 ohm as current is in this direction, it enters here plus and then minus. Now applying KVL to mesh 1, see, algebraic sum of EMFs and voltage drops in a closed loop is 0, that is KVL. In this 4 ohm resistance, as current is flowing from positive to negative, voltage drop is there, so minus 4 into I1. Then next in 2 ohm voltage drop is minus 2 into I1. Then here current is flowing from positive to negative, that is fall in potential, therefore minus 50. Then in this 5 ohm I1 is going in this direction while I2 is in the opposite direction. So as it is resistance, voltage drop is there 5 into the difference of these two currents. As we are in mesh 1, I1 is to be written first, I1 minus I2 is equal to 0. While simplifying this equation, we will get 11 I1 minus 5 into I2 is equal to minus 50. Let this is equation number 1. Next, when applying KVL to this mesh 2, here in 6 ohm voltage drop is there, minus 6 into I2. Then in 5 ohm I2 is in this direction while I1 is in opposite direction, so the total current is the difference. As it is resistance, voltage drop is there, minus 5 into, as we are in mesh 2, I2 is to be written first, minus I1. Then in this 50 volt voltage source, it is rise in potential, negative to positive, so plus 50. Then voltage drop in this 8 ohm is minus 8 into I2 is equal to 0. Simplifying this equation, we will get minus 5 I1 plus 19 I2 is equal to 50. This is equation number 2. Solving equations 1 and 2, we will get I1 is equal to minus 3.8 ampere and I2 is equal to 1.63 ampere. From this figure, V plus 4 into I1, plus is because it is rise in potential, then here minus to plus, rise in potential, plus 6 into I2 is equal to 0. Substituting the values of I1 and I2, V plus 4 into I1 is minus 3.8 plus 6 into 1.63 is equal to 0. Solving this one, we will get V is equal to 5.43 volt. So earlier in case 1, when excitation and response are not interchanged, we got the value of V as 5.43 volt. When we have interchanged the excitation and response, here also we got the value of V 5.43 volt. Since voltage remains the same in both cases, reciprocity theorem is verified. In this example, we are asked to find value of R in the circuit given below. So here this 60 volt is the excitation and our response is this I, which is 2.5 ampere. It seems to be a bit difficult to find value of R by any of the combinations we have studied earlier. So let us apply this reciprocity theorem, in which we will change input and output, that is excitation and response we will interchange. After applying reciprocity theorem, our circuit becomes like this. See, the excitation came here and response is in this side. With this circuit, we have to find value of R. See here, this 10 ohm and this 10 ohm are in parallel. That can be drawn as like this, and it is given that a 2.5 ampere current is flowing through one resistance. As both resistances are the same, total current coming here will be dividing equally into 2. That means current in this 10 ohm also will be 2.5 ampere. That means the total current coming here is the sum of these two, that is 5 ampere. So in this drawing we can mark this current also is equal to 2.5 ampere. That means current coming from this 60 volt battery is 5 ampere, which is distributing equally as 2.5 and 2.5. See here, if you are seeing the total input resistance from here, total input resistance R in is equal to total voltage, that is 60, divided by total current, that is 5, which is equal to 12 ohm. So see, in this circuit, R in is equal to, we got as 12 ohm, which is the combination of this unknown resistance R in series with that 10 ohm, which is in parallel with 10 ohm. That is equal to R plus 5. That is R plus 5 is equal to 12. Therefore, R is equal to 12 minus this 5. 12 minus 5, which is 7 ohm. I think this class also might have been useful to you. If you found any difficulty in understanding any terms used in this class, you can refer to my previous classes, the links of which are given below. Thanks for watching. Please like it, share it and subscribe it by pressing the bell button, so that you will be getting all the notifications of my future videos also. See you next time. Bye.